Part 284C3M1b7C8E13C9C6D3p38d2. This is line 22f1fa19c3m1b7c8E13c9c6d3p38d2 vector finite magnetic nodes UFO 5G Wow Seti. Here's our alien radio signal, and my dad has moved over this way, so I gotta go like that. Okay, so this is a magnetic field nodes, vectors for UFO spaceship and elevator design from the WOW data. February 21st, today's the 24th. Keywords vector finite element method are from line 22f1fa19c3m1b7c8e13c9c6d3p38c. Vector finite element method 5G Wow Seti. And line 22f1fa19c3m1b7c8e 13c9c6d3p38d1. Time vector wave method formula 5G Wow Seti. So our keyword is vector finite element method, a quote from blog. The vector finite element method, originally only the so-called node finite element analysis that has been used. By the node finite elements, the unknown field values are assigned to the element vertices. It is obvious that vector field quantities can be described with their components on the vertices. Thus, node elements can be used also for vector field calculations. In this case, 2 or 3 scalars must be assigned to each vertex, for the 2 or 3 dimensional case respectively. Unfortunately, using the coordinates of the vector gives problems. For example, the continuity requirements for the approximated vector fields cannot be easily fulfilled, and also applying of the boundary conditions is very cumbersome. To overcome these obstacles, the so-called edge elements are used by the vector finite element analysis. They are assigned to the edges of an element and are excellently suited for numerical solution of partial differential equations for the field intensities derived from the Maxwell equations. However, the popular belief that edge elements eliminate the problems with the so-called spurious modes is erroneous. Spurious solutions are avoided by only a proper finite element formulation, and that's from www.iue.tuwin.ac.at. Sounds almost exactly like the wiki one, didn't it? Okay, so quote from blog. Here's a diagram. You can see the hx or hy going straight up, and then x going to the right and y going to the left. So figure 8.5, a transverse magnetic field component is represented by a patchwork of bilinear lowest order basis functions, each living a rectangle covering the x minus y plane, or x to y plane. I don't know how you say that. Okay, the technique represents the electric and magnetic fields as simple piecewise functions over many elements or regions, subdividing a slice through the guide and surrounding the media in the xy plane, therefore by a finite number of degrees of freedom. Each element has a dielectric constant associated with it, allowing arbitrary stepwise refractive index distributions in the xy plane to be modeled. Maxwell's equations for propagating solutions of the form. There's the equation there, are reduced to a generalized sparse eigenvalue equation with that equation there, as the eigenvalue in the bound mode field distributions as the eigenvectors. For introductory reviews of electromagnetic waveguide bound mode techniques, see Sylvester and Ferrari and Davies. Specifically, we use the technique of Fernandez and Liu with hx and hy. As the field degrees of freedom, for simplicity, using first order bilinear functions to represent these fields over each element in a 2-dimensional grid. To reach a compromise between flexibility and ease of coding, the grid of elements was chosen to be non-uniform, in order to allow high densities in the regions where fields change rapidly and low densities in others, but rectangular and separable into a product of elements in the x and y directions. Shows an example grid used for calculation. I don't know if I didn't have that figure. So this is www.math.dartmouth.edu. So keyword photonic crystal fiber will be in the next video. Thanks for watching.